Hello students! This lesson is part 2 of a two-part series on trigonometric identities. We begin with the double angle identities for sine and cosine. Like the last lesson, these red numbers are referring to the identities on a supplemental formula sheet, seen here. And this lesson will focus on the identities in this portion of our summary sheet. Identity 17. The sine of 2 theta is equal to 2 sine theta times cosine theta. We will take a moment and show where this identity came from by using previous identities to create the two identities above. So let's begin with the sine sum identity, where the sine of a sum of two angles, alpha plus beta, is equal to sine alpha cosine beta plus cosine alpha sine beta. If I take this identity and I change both alpha and beta to the same angle theta, then all the alphas and betas on the right side of the equation will also change, and we wind up producing the following. Theta plus theta is just 2 theta, so we have sine 2 theta is equal to sine theta cosine theta plus cosine theta sine theta. These two expressions are identical. Sine times cosine is equal to cosine times sine, and so they can be added together, and we have two of them. And we've established identity 17. So the important thing to note here is that whatever this argument is, these arguments are half of it. Or whatever these arguments are, as long as they're the same, this argument is double it. So for example, if I begin with the sine of 70 degrees, and I use this identity, then each of the arguments on the right side of this identity will be half of 70 degrees. Or if I start with the expression on the right where I have 2 sine of 5x times cosine of 5x, as long as these arguments are the same, then the argument on the left side of our identity needs to be double 5x, which is 10x. And if this 2 wasn't there, and you wanted to use the identity, you would simply need a 1/2 on this side. Now this identity is officially called the double angle identity for sine, but depending on how you use the identity, sometimes your angle needs to double and sometimes it needs to be cut in half. If you use the identity this direction, then the angle's cut in half. If you use the identity this direction, then the angle's double. So it's really a matter of perspective. But officially, this identity is called a double angle identity. Now identity 18. The cosine of 2 theta is equal to cosine squared of theta minus sine squared theta. This looks very similar to the Pythagorean identity, except this is subtraction, not addition. And because it is subtraction, it does matter that you have the cosine first and then the sine second. Let's prove identity 18 by beginning with the sum identity for cosine. The cosine of the sum of two angles, alpha plus beta, is cosine of the first times cosine of the second, and then minus sine of the first angle times sine of the second angle. So again, change all of the alphas and betas to theta. And rewrite theta plus theta is 2 theta, and then of course cosine theta times another cosine theta is cosine squared, and sine theta times sine theta is sine squared of theta, giving us cosine of 2 theta. Parentheses aren't really needed, but they do make things clear that the argument is 2 theta is equal to cosine squared of theta minus sine squared of theta, and that gives us identity 18. Again, as a matter of perspective, if you use identity 18 this direction, then the angle's cut in half. If you use it this direction, then the angle's double. But this is officially called the double angle identity for cosine. For example, if we had the cosine of 30 alpha, and I wanted to use this identity, then I need to cut this angle in half for each of the arguments on the right side. So I would have a 15 alpha as the argument of cosine squared, and the same for sine squared. If I started with the right side of this identity, such as cosine squared of pi twelfths minus sine squared of pi twelfths, these arguments do need to match for this identity to be used, and this will be equal to the cosine, and then we double pi twelfths. And doubling pi twelfths gives me pi sixths. Using the double angle identity for cosine. Suppose that cosine alpha equals 0.6 with alpha in the fourth quadrant. Find the value of cosine 2 alpha without the use of technology, then use technology to find the value of alpha and confirm your answer. So I'm going to draw a fourth quadrant angle, alpha, and I'll use a positive alpha to get there, although you could easily use a negative alpha instead, and the identity will still hold. Furthermore, we know the cosine of alpha is 0.6, 6/10, which I could reduce to 3/5, and I want to think of that as adjacent over hypotenuse. So making a right triangle with the x-axis involved, the horizontal leg would be 3, and the hypotenuse would be 5. Let's wait to compute the opposite if we determine that it is needed. So now we want to find the cosine of double alpha, which means imagine doing an alpha rotation one more time and sort of guessing where that would wind up. Well, instead of trying to make a new triangle and then answer the question that way, we're going to use this double angle identity. The cosine of double this angle will be equal to cosine squared of this current angle for which I have a triangle drawn minus the sine squared of that same angle alpha. So the cosine of alpha needs to be squared. Cosine of alpha was given. I'll use the fraction form of it, 3/5. So 3/5, and then we square, minus, and then the sine is opposite over hypotenuse. So it turns out I do need to figure out the opposite. Calling it b temporarily, we know that 3 squared plus b squared will be equal to the hypotenuse squared. So b squared will be equal to 25 minus 9, which is 16. Therefore, b is plus or minus 4. And because we're in the fourth quadrant, we need b to be minus 4. So the sine of this angle alpha using this reference triangle is the opposite over the hypotenuse, but then that needs to be squared, which means that I could have mistakenly said that b was positive 4, and in this case it would not have mattered. So we get 9/25 minus 16/25, which gives me a negative answer, negative 7/25, suggesting that if you double the angle alpha, I should wind up either in the second or third quadrant, because that's where cosine is negative. Now we will use technology to actually find out what alpha is. If I do an inverse cosine of 3/5 and call this angle theta, keep in mind that the inverse cosine will only give us angles in the first or second quadrants. So using Desmos, I type in arc cosine of 3/5, or I can say cosine to the -1 of 3/5. Pick your mode, degrees or radians. Let's go with degrees on this. And notice I get about 53.13 degrees. We'll just say 53.1 degrees, which is a first quadrant angle. So it's clearly not equal to the alpha I'm looking for. But the negative of theta would be the negative arc cosine of 3/5, which would be about negative 53.1 degrees. This is an angle that is coterminal with my angle alpha. I assumed that alpha was a positive angle, although we could have used this negative angle to begin with as alpha. But given my drawing, let's go ahead and find out what alpha actually is. So we just have to rotate from negative theta counterclockwise one full rotation. So to find alpha, we will begin with negative theta and add to it 360 degrees, which gives about 306.9 degrees, which is a positive fourth quadrant angle. So let's make this angle negative and then add to it 360, and I'm going to call this A. And now to check our work, let's go ahead and do the cosine of twice this angle, and we get negative 0.28. And a moment ago, we said that our answer should be negative 7/25, which is the same result. So this confirms our use of the double angle identity. Okay, let's go to the next page. Here we have two identities known as the half angle identities for sine and cosine. We will take a moment to establish these identities by using previous identities to create them. Let's begin with identity 22. And I'll begin with the double angle identity for cosine. But there's a sine squared sitting right here and a cosine squared. Identity 22 involves sine squared. So I'm going to use a version of the Pythagorean identity on cosine squared. Here's the Pythagorean identity, and one version of it is that the cosine squared is equal to 1 minus the sine squared. So that gives us cosine of 2 theta is equal to, and replace cosine squared with 1 minus sine squared, and then of course we have another minus sine squared. This gives me cosine 2 theta is equal to 1 minus 2 sine squares of theta, and now I will solve this equation for sine squared. So let's add the 2 sine squared to the left side of the equation, and subtract the cosine 2 theta to the right side of the equation, and now divide everything by 2. Or you could distribute the 1/2, or write this as 1 minus cosine 2 theta all over 2. It doesn't matter which variation you use. So sine squared of 7 degrees would be equal to 1/2 times, and then to go from this argument theta, and to use this identity, we would need to double that angle as the argument for the cosine. So we have 1/2 times 1 minus cosine of 14 degrees. So again, this is a matter of perspective. If I use the identity this way, the angle doubles. But if I use the identity the other way, the angle cuts in half. But formally, this identity, as well as identity 23, are known as half-angle identities. Let's establish identity 23. This time I will use the Pythagorean identity on sine squared. So we get cosine of 2 theta is equal to cosine squared theta, minus, and then use some parentheses, sine squared is equal to 1 minus cosine squared. That is the Pythagorean identity, which we also used before, but a different variation of it. Okay, let's distribute the negative across those parentheses, combine the two cosine squares, and solve this for cosine squared. I'll add 1 to the other side, divide both sides by 2, and write cosine squared first, giving us identity 23. I could create a variation of this by doubling both sides, which would take me to this line, and then subtract the 1 over, taking me to this line. So here's one variation of this identity. If I use identity 23 this direction, the angle needs to double, so we go from theta to 2 theta. But if I use the identity in the reverse, the angle cuts in half. 2 theta becomes just theta. Or I could just use this variation. For example, if I had the cosine of pi fifths and I wanted to use this identity backwards, I'll use this variation here and write this as 2 times cosine squared. And then to use this variation, we go from angle 2 theta to angle theta. So the angle needs to cut in half. And if I take pi fifths and cut it in half, which is pi fifths times a half, which just gives me pi tenths. On our summary sheet, this process of going from identity 18 to identity 23 is right here. And along the way, it includes these variations of these identities, which we'll call identities 19 and 20. Okay, let's go to the next page. Using the half angle identity for sine, find the value of sine of 22.5 degrees. Well, ask yourself, if you double 22.5 degrees, does it become a convenient angle? And the answer is yes, because it becomes 45 degrees. But if you cut 22.5 degrees in half, it becomes 11.25 degrees, which is not a convenient angle. At least it's not an angle on the unit circle. So I see value in doubling this angle. So we will use an identity that begins with the sine of an angle and allows me to compute the sine squared of that angle by doubling the angle and then finding cosine of it instead. So we know that the sine squared of 22.5 degrees can be equal to 1/2 of 1 minus the cosine, and then double this angle to 45 degrees. And now I can use the unit circle to help me with cosine 45 degrees. That will be radical 2 over 2. And now we want to get rid of this square by taking the square root of both sides. When you do so, you'd normally have plus or minus, and you could distribute the 1/2 through these parentheses, which I'll do in the next step. But we need to decide, do I keep the plus or the minus? And so knowing which quadrant we are in will help us make that determination. The 22.5 degrees is a first quadrant angle. Therefore, the sign needs to be positive. And if I do distribute the 1/2, we get this radicand. Let's confirm this one with technology. When you do this, make sure that you are in degree mode, and you can see that we have confirmation that the answer we got is in fact equal to the sine of 22.5 degrees. Right, next slide. Let's use the half angle identity for cosine. Suppose that alpha is an angle in the third quadrant such that tangent of alpha is 0.6. Find the value of cosine of alpha halves. So the tangent of alpha is equal to 0.6, that's 6/10 or 3/5, and tangent is opposite over adjacent. So let's draw a picture of alpha being in the third quadrant. Again, I'll assume a positive value of alpha to rotate to this position. Make a reference triangle and label our opposite and adjacent. Well, we're in the third quadrant, so they both need to be negative, but the tangent will still be positive 3/5 because a negative divided by a negative is a positive. We will find the hypotenuse if necessary. Now we're asked to find the cosine of alpha halves. Now if alpha is in the third quadrant, then half of alpha would have to be somewhere in the second quadrant. Keep that in mind. But I don't have a reference triangle drawn for alpha halves, but I do have a reference triangle drawn for alpha because of this information that was given. So I effectively want to double alpha halves to alpha, which is where the half angle identity for cosine comes in, because if you have an angle here and you use this identity, that angle doubles. So according to the identity, we get cosine squared of alpha halves is equal to 1/2 times 1 plus cosine, and then double alpha halves, which turns the argument to just alpha. So I can use the reference triangle I have here to do that part of our identity. So cosine squared of alpha halves is 1/2 times 1 plus, and I have to do the cosine of alpha, which is adjacent over hypotenuse. So I do need to find the hypotenuse. Let's call it C for now. We know that negative 3 squared, which is 9, plus negative 5 squared, which is 25, needs to be equal to C squared. So C is the square root of 34, and only keep the positive answer here. When we make these reference triangles, regardless of which quadrant we're in, we always assume the hypotenuse is positive. It's only the legs that can be negative depending on the quadrant. So the cosine of this angle alpha is the adjacent over the hypotenuse. So you have cosine squared of alpha halves is equal to, I will distribute the 1/2. This becomes subtraction, 5 over 2 radical 34. And now we need to take the square root and decide whether we will have a positive or negative answer. Which of these two signs do I keep? Well, since alpha was in the third quadrant, we know alpha halves has to be in quadrant 2, which means I need to keep the negative because the cosine is negative in quadrants 2 and 3. And this would be our result. If we were to confirm this with technology, we could find alpha first using an inverse tangent, the inverse tangent of 3/5. Making sure you are in degree mode, the arctangent or inverse tangent of 3/5 is about 30.96 degrees. This is a first quadrant angle, which in this picture would be extend this hypotenuse into the first quadrant, and we get this orange angle theta. Well, theta is not alpha, but if I add 180 degrees, I will get alpha. So I get about 210.96 degrees. Let's call this angle A, and now let's do the cosine of half that angle, and let's check this against our answer, and notice we get the same decimal representations, confirming our work. Okay, next page. Here we have the double and the half angle identities for tangent. The double angle identity is identity 21, and the half angle identity is identity 24. But again, depending on your perspective, if you use identity 21 in this direction, the angle cuts in half because we go from 2 theta to thetas. Whereas in this direction, if I begin with thetas, the angle doubles to 2 theta. Same over here with identity 24. In this direction, the angle theta doubles to 2 theta, and there's some cosines involved here. But using the identity this direction, the angles start at 2 theta and become theta, so they cut in half. So it's really a matter of perspective. But officially, identity 21 is called the double angle, and 24 is called the half angle. We will use previous identities to create the two identities above. So in a previous lecture, we had talked about the tangent of alpha plus beta is equal to tangent alpha plus tangent beta divided by 1 minus the product of the tangents. Take this identity and simply change all of the alphas and betas to theta. That would give us tangent 2 theta is equal to tangent theta plus tangent theta over 1 minus tangent theta times tangent theta, which gives us simply 2 tangent thetas over 1 minus tangent squared of theta. And this is identity 21. Now for identity 24, I'm actually going to begin with a basic identity for tangent squared. Tangent squared of theta can be found by doing sine squared of theta divided by cosine squared of theta. And now I will use the half angle identities for sine and cosine, identities 22 and 23. For sine, it's 1/2 times 1 minus cosine 2 theta. And for cosine, it's the same, but addition. Now these 1/2s just cancel each other, giving us identity 24. Let's use both of these identities on the next page. Given the triangle below, find the indicated values. So we have a right triangle. This angle is alpha, this angle is beta, and we know the two legs. So we know that the tangent of alpha is opposite 2 divided by adjacent 3. But tangent of beta, the opposite and adjacent roles reverse. We get the opposite of 3 divided by the adjacent 2. One of our goals is to find the tangent of double alpha. Well, you might think that if alpha rotates this much and you double that this might produce a new reference triangle whose opposite is double this number, 4. But it turns out that's not true. The height of this new reference triangle is unknown. Every time we increase by 1 degree, we actually gain more and more vertical because the angles get steeper and steeper. In fact, if alpha was 45 degrees and we doubled it, we would actually wind up with an angle pointing straight up, which would not be a reference triangle where the opposite got doubled. But instead of trying to create a new reference triangle for double alpha, we can just use the identity. Tangent of 2 alpha is equal to 2 times the tangent of alpha, using this identity but with alphas instead of thetas, and then divided by 1 minus the tangent squared of alpha. And we know the tangent of alpha is 2/3. So we get 2 times 2/3 over 1 minus the square of 2/3, giving us 4/3 divided by 1 minus 4/9, giving us 4/3 divided by 5/9. Invert and multiply. We have 4/3 times 9/5. I can cancel this 3 into that 9, leaving a 3, and in the end we get 12/5. Now if I wanted to make this have a denominator of 3, since that's the adjacent in this image, I could multiply top and bottom by 3/5 to rewrite my fraction this way, 36/5 over 3. We don't need to do this, but this is what I would do if I wanted to ask myself, if I did actually double alpha and make a new reference triangle, and I kept the adjacent 3, the new opposite would have to be 36/5. And that is not the result of doubling 2. So you want to be careful. A common mistake is to say that the tangent of 2 alpha can be found by simply doubling the tangent of alpha. And this is a big no-no. The same is true for sine and cosine too. Be careful you don't make any of these mistakes. And now let's do the tangent of beta halves. My reference triangle involves beta, not beta halves. But if you cut that angle in half and made a new reference triangle, this would still be 2. But the question is, what would this side be? Now be careful, you do not assume that it's going to be half of 3. In fact, it won't be. But it'd be nice to be able to find tangent beta halves by using the reference triangle involving beta. So I would like to double beta halves using an appropriate identity. That's going to be our half angle identity for tangent, because we have an angle theta, and then it gets doubled if I use the identity. So to evaluate tangent of beta halves, it would be convenient to double the angle to beta so I can use the reference triangle. But also notice that there's a square on the tangent. So I'm going to apply this identity by putting a square on this tangent, and we have 1 minus the cosine and then double beta halves to beta over 1 plus cosine beta. Now relative to beta, 2 is the adjacent, radical 13 is the hypotenuse, so the cosine of beta is 2 over radical 13. Now an easy way to simplify this complex fraction is to multiply top and bottom by the LCD, or lowest common denominator, of the little fractions, which would be radical 13, over itself. And then distribute, and we get radical 13 minus 2 over radical 13 plus 2. Now this fraction is equal to the tangent squared of beta halves. So now I want tangent of beta halves, which I will get by square rooting. And then keep in mind that beta is an acute angle, so if you cut it in half, it'll still be acute, which means in standard position would be a first quadrant angle. And all trig functions of acute angles are positive. So keep the positive radical, and we are done. And this concludes part 2 of a 2-part series on trigonometric identities.